but it's more of a formalization of deformation theory. But still, let me just take this opportunity to thank everyone, the organizers of the program, and in particular Bruno for all the effort that was made. So a round of applause, please. Very good. It's everyone's.
It's a pleasure to see all of you here, smiling and bring life to mass.
It's a pleasure for everyone, I think. So the goal today is to talk a bit about this this formalization of deformation theory, and let me start with some classical example. Which is the deformation of complex varieties, and so we take X, a complex variety that we maybe need to suppose that it's proper, smooth, complex variety, and the idea is that if we want to study infinitesimal, so study infinitesimal deformations, deformations along local Artin ring or algebra. So just for the moment, okay, now we're over the complex numbers, but I will explicitly say if at some point we ever leave characteristic 0. So this is a constant for now. And we're deforming along a local Artin ring A, and the picture to have in mind is you have your you have spec of A, so you see A as the deformation parameter, and spec of A is kind of the space of parameters along which you're deforming, and it's local, so there is this special point in there, so spec of C, and the idea is that you have some sort of family of deformations that are parameterized by the space, so that the fiber at each point gives you a deformation, and you want that when you restrict to the special point on a spec of A, you recover that Blackboard management. You recover X. So if you do this pullback, you get back X. So this is a very classical story, and I think dates back to Kodaira and Spencer from the 50s or 60s that tell you that in some sense, infinitesimal deformations are controlled, governed by the tangent bundle of X in the following sense. So there are some if you take cohomologies with values in the tangent bundle of X, so okay, maybe in cohomology 0 you get some automorphisms, some first order automorphisms, and then in cohomology 1 of in degree 1 of this cohomology, you get kind of deformations of X along C of epsilon over epsilon squared. So these first order deformations, and this correspondence is given by the Kodaira-Spencer map. But it gets more interesting than in degree 2, because in degree 2, what you see is some obstructions to lift deformation. So obstructions to extend deformations to higher order. It's okay? Oh. Great. So in the following sense, if you take an nth order differential deformation on X, so something that is given by this map into spec of C epsilon modulo. So if it's of order n, should be modulo n plus 1. And this you can do the opposite of the no, sorry. So if, yeah, let's just do it like this so that I don't get lost in my notes. So let's say it's a deformation of order n plus 1. Then you map this into spec of C epsilon over epsilon n plus 1. Now you can wonder whether you can lift this so n minus first order deformation to a higher one. So if you can complete this square such that when you restrict back, you recover your original deformation. So it turns out that the existence of this is equivalently given by some obstruction classes that live exactly in there, in H2 of X dx. And the idea that we've been kind of seeing throughout this lecture series is that this is deformations are Lie algebras, right? So it turns out that this cohomology, so this cohomology is computed by this Dolbeau complex. So A of 0 bullets of dx, and or maybe let's just call it omega, which is a DGLA, and so a DGLA living in positive degrees, in non-negative degrees, and what one realizes is that the deformations of X are in correspondence with the Moore-Cartan elements of exactly that thing. And under this correspondence, automorphisms here are in correspondence with the actions of the gauge group. So the gauge group is the algebra as we've seen all this time. And yeah, so essentially all obstructions are encoded by this CGLA. And what you might wonder, or maybe not anymore after Alexander's lecture, is so the fact of being a more Cartan element and of having gauge equivalences and everything is something that takes place in a very limited number of degrees. And because, well, the more Cartan elements live in degree 1, the gauge group lives in degree 0, and the more Cartan equation lives in degree 2. So this lives in positive degrees. So there's just the question of what exactly do the rest of the positive degrees do, and what they do is they control some sort of derived deformations, and this inspires the following definition of trying to not only deform along ordinary, like classical algebraic geometry, say, but deforming along more derived spaces. So what one introduces is the definition of differential graded Artinian algebra, or rather, so the category that I will denote by art over K. So, okay, we left complex geometry. This was a bit just the classical situation. Now we're always working over a field of characteristic K, of characteristic 0. The category art K of differential graded Artinian algebras is so it's a subcategory of augmented commutative algebras, and it's defined in a more or less inductive way. So is the smallest subcategory of commutative algebra, so augmented, such that so the sort of infinitesimal lowest order infinitesimal algebras such as K epsilon modulo epsilon square are small, but also the ones that don't live necessarily in degree 0. So sorry, this plus K epsilon. So this two-dimensional algebra K epsilon, but this one living in degree minus n, and this living in degree 0, is small. So just degree n. This is the identity, the unit of the algebra. My writing is getting smaller. Thank you. So I need to work with big yes. So also, small is not even the word I wanted to use. I wanted to use Artin. But you'll see soon why I made the mistake of writing small. And so that this is that these ones are Artinian, and it is closed. So the category is closed under square zero extensions, but you need to take them in the appropriate sense. So under pullbacks, backs of the form A K plus K epsilon N. Oh, sorry. So all of these algebras are in degrees, are in negative degrees. Yeah, so I'm defining the category of art K inductively. So I'm saying these algebras are artin, and furthermore, you square zero extensions of artin algebras are artin algebras, and this is what I'm doing now. So if you take, it's fine. You should ask as many questions as you want. So if you take a homotopy pullback over such an algebra, if A small, so this should be a homotopy pullback. So A small, A artin. Sorry. Sorry? No, I mean 0. So homotopy. Sorry. Yeah, sorry. Of course, this is not augmented. 0 is not augmented. Yeah. Cohomological degrees. So these will all live in at least cohomologically negative degrees. So A is artin will imply that this pullback is artin. So somehow it's a good notion of algebras that you want to consider infinitesimal deformations along. Now, this is not in principle very useful if you cannot describe them more concisely. So there is this, you can show that an Artinian an algebra is Artinian. An Artinian algebra A. Homotopy pullback. So in commutative algebras, you need to take the appropriate resolution of this map. So let's say an augmented to differential graded commutative algebra A is Artinian if the following conditions apply. So one, its homology is concentrated in negative degrees, in non-positive degrees. If I bigger than 0, then 2, the total cohomology is of, so let me just write total finite dimension. So not only each one of them is finite dimensional, but you can also not go in infinite to minus infinity in degrees. And furthermore, the Artinian condition is that the kernel of the augmentation map, at least in homology, is nilpotent. Right. So it's an if and only if. So it's a full description. So practical definition, kind of a more motivational definition. So Right. So I guess what I should have actually written here is you always need to know what you're deforming along. So if I want deformations of x along the Artin algebra A, here I should be considering the maximal ideal, the unique maximal ideal generated by A. So we're doing things over a field, so it's really just an augmented algebra, so it's the kernel of the augmentation as well. But of course, if you work in if you're working in the classical sense, this is concentrated in degree 0, so you still have this sort of degree phenomenon that looks a bit like there's just a lot of information being discarded. But now that if you try to do the same and put here a DG or Artinian algebra here instead, so they live in negative degrees. This one lives in positive degrees, so their tensor product can end up all over the place. So you do see the higher degree terms playing a role in this story. What one might actually ask is, well, then, since Artinian algebras live in negative degree, at least homologically, now if the Lie algebra is negative degree, then we also don't see it. But I think we've seen already, especially in Alexander's lecture and all this Mark-Artin functor, then at some point you tensor up with some differential forms that live also in positive degrees, so it also takes contributions from negative degrees. So in some sense, negative degrees control homotopies between deformations. Okay, so is there a question? No. Okay. So we're now ready to define the notion of a formal moduli problem. So the most important notion of today. Formal moduli problem. So the yes.
So in your conventions, you have for instance, there you have.
Let me just write once and for all that the degree of my differential is +1.
So if I understand correctly, in your convention, you have the positive homology of this GLA, which controls the deformation in the successive absorptions.
So it's morally heuristically positive cohomology controls derived deformations, whereas negative cohomology controls homotopies between
so the
deformations.
Other side is the infinity group, and the upper side is somehow the smooth side.
Yeah, I mean, at this level of vagueness, I agree with everything.
Okay.
Yeah. Right. I mean, at the end, everything will kind of, yeah. So a formal moduli problem. So by the way, Artin, whenever I say Artin from now on, I mean DG Artin. So this will never, everything will be DG from now on. So is a functor F from this category of DG Artin algebras, okay, to spaces satisfying some properties. But before even stating the properties, I think some remarks are in order. So the idea is that it's the sort of Grothendieck functor of points perspective on things. So the idea is that to an algebra, you associate to it the space of deformations. But one thing that there is no way to go around in this story is that we need to be dealing with the infinity categories. So this will actually be a functor infinity categories. But much like Geoffroy, we can essentially, for the entire of this talk, work with a very intuitive notion of what this is meant. So we just interpret everything as we're doing things that make sense only homotopically. So for instance, if we see pullbacks, they will always have to just be homotopy pullbacks, etc. So I'm also being slightly vague with what I mean by spaces, but the intuition is the right thing if you want to be a bit more precise. So this will be an infinity groupoid. This will land in infinity groupoids, but I think this will be fine. So what we require from a functor of infinity categories to be a formal moduli problem. That, by the way, I will probably never write formal moduli problem again, and I will just write FMP. Is something that requires first a normalizing condition, which is if you're deforming over a point, which in the Artin case means just if you deform over the trivial, the algebra, the unital algebra K. So this has to be the point. But of course, in the infinity categorical sense, this needs to be a homotopy equivalent to a point. And then there is so it satisfies only two properties. Then there is a second property, which is the so-called Schlesinger condition that gives you some compatibility between the formations. So what it tells you is if you take Artin algebras A1, let's say A0, A1, A2 in DG Artin, and with maps A1, A0, A2, and we take their homotopy pullback. So is this still visible? I'll try to write bigger. And we take the homotopy pullback of 3 Artinian algebras, but with just one additional assumption. So we require these maps to be surjective in H0. So if furthermore the zeroth cohomology of AI into the zeroth cohomology of A0 is surjective for the 2 I's, I mean, I guess for the 3 I's. If this map is surjective, then pullbacks are sent to pullbacks. So then F of this pullback is given. So there is a natural map, first of all. In general, you have a functor. There's a natural map from F of a pullback into the pullback of the images. So A1 cross F of A2 over F of A0, and you require this map to be an equivalence as well. So the image to have in mind is that, well, you have here your space, and what we're saying is, well, if we can deform along this neighborhood, and because so you should kind of take spec of this diagram, and you see something like you have 2 neighborhoods that agree on kind of spec of of A0. And if you can deform here and you can deform there and that these deformations coincide, then you can just deform along their union glued along A0. Of course, maybe this picture is a bit tricky because these are infinitesimal deformations, so maybe we should not think of this as open sets, but rather as infinitesimal closed sets. So it's maybe more, if you can deform north and you can deform east infinitesimally, then you can deform in these 2 dimensions. Okay. So I should present I think the most important theorem in the last decade from in deformation theory, maybe, which is in a way the thing that we've been saying all along. So it's a theorem due to Lurie and Rhythm independently, which tells you that, so first of all, formal moduli problems are functors, so they determine an infinity category as a subcategory of a functor category. And Lurie and Pridham tell you that there is an equivalence between the category of formal moduli problems and Lie algebras. So there is infinity categories. So from this infinity category and this one that is slightly more manageable because it's the infinity localization of a model category. So it's the formalization of this slogan that I started this lecture series with. Right, and one can talk a bit about the way that this equivalence is established, but I will postpone this to a later point and make the connection with the previous story. So, you know, relation with 2 previous lectures. And with operatic deformation theory. So take the following. Suppose you have so I'll try to keep A for Artinian for the Artinian algebra. So suppose B is an associative algebra. And so I'll describe now a formal moduli problem associated to B. So I will denote, so I'll define deformation of B, a formal moduli problem, which, so it should be a functor from Artin algebras to spaces. And deformations of, so A in Art K. I define the deformations of B evaluated at the algebra A as a following pullback. So first I have B that lives in the category of associative, say, K algebras. So B is a point here. So I see B as a point there. And now what do I want to do? I want to deform the idea is we're deforming the algebraic structure of B along this space of along these parameters A. So what I can do is take associative algebras. So imagine if A is I don't know epsilon square, you would like to take associative algebras in so associative A algebras. Now it turns out that you want that your deformation of A, whenever you restrict back to 0 somehow, you recover your algebra B. You want it to be a deformation of this B. So you take the thing here that will send an algebra, let's say B parameterized by A to B parameterized by A, and you tensor it with K over A. So and then you take this homotopy pullback. Now then it turns out that you can identify essentially deformations B of A with exactly the set of algebras, A algebras, BA together with an equivalence BA tensor KA back to B. But so this is in infinity categories. You're not just requiring that this gives you back B. You're actually just prescribing an equivalence between the two. And in principle, where is this fiber product being taken over? It's been taken over infinity categories, but one actually verifies that the infinity category you obtain is actually a space. So that's it. You have, and okay, so I guess the fact, the proposition is that def B is indeed an FMP. And now we ask, well, under this equivalence, what's the Lie algebra it corresponds to? And you'll believe that we were actually doing something related in the previous lectures to this one. If I tell you that under this equivalence, def B is encoded by the Hochschild cochain complex or Lie algebra of B, so with values in itself, which I was previously denoting by G of infinity B, I believe. But sorry, just one thing. So B is an associative algebra, and there is a multiplication mu B tensor B to B. So according to my previous notation, this answer? Yes, so B lives in K algebras. There is no way yet. There is no way. Yes, it's a tensor over K. So only BA will even have any relation with A. So here, according to the previous notation, it's this twisted by the Mora carton corresponding to the product. So the GLA with this Kersenhaber bracket in the particular Hochschild case, you will not, I think, be terribly surprised if now I start putting operads and saying that it just works exactly the same. So instead of an associative algebra, you take a P algebra. Let's maybe assume that P algebra, just to make sure that there's no technicalities, we say that P is Koszul. Here it's fine. Here it's the same thing. Here it's you replace it by P algebras in A modules, and then you would replace this. Lower left corner of the diagram, this one? Yes, of course. Of course. And here you would get instead, so G of P infinity be twisted by a certain Mora carton element that determines the structure. My last lecture was already 3 days ago, so let me just remind you the form that this guy has. So it's some product for n bigger than 0 of P Koszul dual cooperad to endomorphisms of the algebra B. Yeah, this maybe I should put some arities, and here these are symmetric maps, and then the twist by the Mora carton element. So okay, so this is the Lie algebra that encodes the formal moduli problem above. Yes. So the question that I would like to try to address is the following. What if G, the Lie algebra, so maybe not in this specific case, but in general, what happens when the Lie algebras you obtain from a deformation problem are somehow richer? So what if G contains some extra structure? Yes? So all my A's, if I don't make a mistake, will be Artin in this talk, and they will be like this. So yes?
What is the notion of being Martin for P?
No, but that's it. It's independent because yeah, Artin is always a commutative algebra, and yeah, you'll recall that tensoring with commutative algebras is very good at preserving structure. Yeah, so on the FMP side, it's always so you always evaluate it on Artin algebras, or Artin differential graded commutative algebras that satisfy some properties. Right. So so let me address the slightly easier example somehow of so let's say that now let C be a commutative algebra, and we're not deforming C. We're taking and M C module. So right, so we can more or less repeat something of the same sort and define deformations of M, and which will be an FMP, such that the deformations of M when evaluated at A is something like B modules in A modules. So let's say A tensor B modules, fiber product, always homotopy fiber products, I guess. Here I should have also put a homotopy. Fiber product with this point representing M, and the point is that the corresponding Lie algebra what? Yeah, me too. No, sorry, it's C. Yes, sorry. Yeah. Sure. Right. So the Lie algebra, let's say the corresponding DGLA is so it's still visible until here. Okay. I mean, for the computer, maybe not for the people here. Yeah. Anyway, the corresponding Lie algebra is, let me just call this one V. It's so it's the derived mapping space of from the derived endomorphisms as C modules. So it's Tom over C of some resolution of V or of M as a C module. So there bar construction CM into the bar construction of CM. So this guy here, it's this construction where you take many copies of C and then you tensor it up with M and it gives you a resolution in a quasi-free resolution in C modules. So anyway, it's this with product. So with bracket given by the composition, the anti-symmetrization of the composition. So you might actually wonder why I had to resolve the target. I don't need to resolve the target, but it just makes it more clear that you can actually compose such things. And so then in this case, it's a Lie algebra, but it's more than a Lie algebra. It's an associative algebra that is inducing the Lie algebra. So actually, Lurie-Prudhomme's theorem can be refined into something more. Because so what you realize is that at the level of the Lie algebra you have some extra structure, but this is also reflected at the level of the formal moduli problem. Because so here in the formal moduli problem you're plugging in commutative algebras, so Artin commutative algebras, but Actually, in this particular case, you can plug in, you don't need to require commutativity. You can plug in associative algebras that are arting in exactly the same sense. And in that case, maybe I should mention that this the original Lurie and Pridham theorem is from 10 or 11 years ago. People talk about it as if it's very, very classical, but it's only moderately classical. It's just a theorem that had very much impact in modern research. So there's a theorem that says that essentially you can also define associative formal moduli problems, which I will just define orally as saying that you take exactly the same definition, which unfortunately I think I erased part of it. So you take exactly the same definition, but you allow your, you just change the definition of arting algebra to take associative algebras instead of commutative, and everything stays exactly the same. Both descriptions are fine, or at least that description is fine. So anyway, then you have a category of formal moduli problems that, let me just, so I think I'm interested in writing the arrow in the other direction. So in this case, there is also an equivalence of categories between this one and now the category of associative algebras. Of course, so differential graded associative algebras. And so exists an equivalence of infinity categories. And furthermore, this is compatible with the first theorem. So in the first theorem, we have an equivalence between Lie algebras and what I will now denote, just to distinguish it, I'll denote it by commutative formal moduli problems.
So here you're saying deformation are not controlled by commutative arting algebra, but something associative with it.
Yes, but so it's stronger. So okay, let me say a few more words about this. This is so. Let's take a step back. The idea of these deformation functors is that they tell you make them eat a space that you picture as a commutative algebra with some properties. It's infinitesimal, and then it tells you how to deform along this commutative algebra. Now, a bit in the spirit of non-commutative geometry, you can also feed it more general spaces. You can feed it a non-commutative space, which will be represented by an associative but non-commutative algebra. So functors here take a lot more values than functors there. So they're you can evaluate it in more spaces. And so in particular, there is a restriction from here to here. So which tells you that if you want to evaluate it, the formal moduli problem in a commutative algebra, well, you know how to evaluate it in every associative algebra, so you just do that. And it turns out that this, well, if you have an associative algebra, we already know how to send it to commutative to Lie algebras, and so not only they show that there is this equivalence, but this square is commutative. And so now what I would like you to, your instinct to be is, well, we're interested in this operatic deformation theory. Our Lie algebras are not really only Lie algebras. They actually have this sort of additional Lie structure that kind of lives in between. So you can ask the question of what's going on here on the other side. There is some caveat that it should still be reminded, which is that so G of P infinity mu, when mu is equal to 0, is Lie. So if you don't twist by any structure, sorry, here usually I have V or something. This is typically not Lie. So the new differential will not respect the Lie product. In particular, also the cohomology is not a Lie algebra, even though, yeah. So what we propose is the following. So theorem definition by Damien Calac, myself, and Joost Nuiten, that states that there exists a good notion of P algebraic FMPs denoted FMP subscript P, yes? No. Subscript P. If P is nice enough, so let's make our lives very easy. Quadratic, binary, causal, and then I guess FMPs over P are equivalent to algebras over the causal dual of P. And furthermore, this correspondence is natural. So this is natural in P.
May I ask why binary quadratic because of the Napoli 2p3 times P?
This is really not a strong assumption. At the end, we can, yeah, just to avoid some technicalities. It's not particularly, it is not particularly important. Yes, it maybe plays a. What did you say for the Lie structure, L infinity structure on the tensor product of?
Because when you have binary quadratic, then P3 times P gets a natural map for me.
Yeah, you don't actually need this because in more generality, one can work with the L infinity map. So actually, in in a bit more generality, this theorem will work. I mean, you don't actually even need Kozel, but then it will just get more cumbersome. So you can replace this by the dual of the bar construction, but whenever there are duals, maybe you need to impose some finite dimensionalities. And I invite you to take a look at the paper for the exact conditions, but it's actually very, very broad. So, yes. Yes, we can talk about this, but I think this is the most economical thing that will say something. Also, in particular, no. It's for the presentation. These assumptions are far from essential. But then, yeah, okay. Maybe I also need to assume that it's finitely generated. It does not have infinite generators. There are some degree conditions as well if you want to go out of the Kozel duality setting. But so before I actually want to define what this is. Okay, we know what P-Schrick algebras are. We do not know what P-algebraic formal moduli problems are. And the biggest obstruction is exactly this notion of Artinian. Because, yeah, maybe, so you can look at this and see that some of the things you can transpose for a more general setting. The nilpotency condition is a bit trickier. So you'd rather be using the other definition. So, so let me. So the reason why I was making a mistake before is that now I want to use an analog of Artinian algebras, but I don't want to call them Artinian for a reason that I will make clear in 2 minutes. But a P algebra is small, or again, let me do a definition proposition because I'll state an equivalence of two different things. So P algebra is said to be small if a couple of conditions are satisfied. So one, the homology of A, so P algebra A. So as before, Artinian algebras were always A. I'll keep reserving A for this space of parameters. Sorry, but until when do I have? It should be 4. Okay. It can be 4:30.
That's straight.
Very good. So the cohomology should be 0 in positive degrees, and it should also vanish for sufficiently small degrees. And 2, it's just finite dimensional everywhere. Is finite dimensional, and then 3. So yeah, let's say that P is always we're always in the setting of P quadratic Kozel because otherwise definitions need to be a tiny bit enhanced. So the last condition, the nilpotency condition, is that Hi of A is nilpotent. So with respect to H0 of A. So concretely, if I take AIs in let's say in homology 0 of A, and P and some operation in P in degree 0, or if P had differential, I actually want to take in the homology of P, then I want that P of A1, AN, N is not being used, right? So I fixed some N's. So this, since everything is in degree 0, this is an endomorphism of H0A to H0A. And I want that there exists, from the beginning, there exists, so fixed A, I want that there exists some K, such that if I iterate K of things of this form, no matter, like I can change P, I can change the AIs, I will get 0 regardless of what I do. No, there exists. Yes, I do. Thank you. So for all I. Yeah, well, I think I was saying that something about degree 0, but I meant this operation has degree 0, so it sends HI to HI. Thanks. So that iterations of this are eventually 0. So no, the K might only depend on A from the start. So like when you have, if your algebra was K epsilon modulo epsilon 7, you know that regardless of what you do, you multiply non-unital things, and after 7 steps, or you'll end up definitely getting 0. So so I don't know. After K iterations becomes 0. Now, I said that this was a proposition definition because the way you can actually make sure that you get the right object is by copying the other definition somehow. So equivalently, the category that I will note by small p is the smallest one containing yes, thank you. It's the smallest subcategory of P algebras containing full subcategory containing the trivial algebras K living in so this is the difference between Artin and not. There are no units. We're doing P algebras. So now instead of having a 2-dimensional thing, I have a 1-dimensional thing. So containing this, so this lives in degree minus n, and it's a trivial algebra in degree minus n for n bigger than 0, and so closed under square 0 extensions exactly in the way before, under square 0 extensions.
There are elements in the narrative of this is non-trivial, and the equation. But it is because it's binary.
I really don't want to talk about RT1. Okay, well, let's yeah. It's from all the things that we can add to this theorem, and the RT1 is one that we can add, but it's the one I have the least wishes to elaborate on. I guess we can talk after the talk, but there is. Yes. Okay. There is worse. I do agree. Yeah. So the remark is it's not hugely important, but it's when in this story when kind of so remark A is an Artinian algebra. Artinian in the sense commutative is Artinian K. So if and only if A mod K, so the kernel of the augmentation is a small commutative algebra. So I'll get vaguer and vaguer about whether things have units or not whenever it's relevant, but it's not a huge deal, right? If you're dealing with augmented or non-unital, everything is the same. Right. So just a word about naturality, which is also why I wanted to restrict to binary causal operads and not just quadratic operads. This allows me to avoid adjectives here. So talk about quadratic data. Naturality. So by naturality, I just mean if I have f from P to Q of, so everything is causal binary. Then we have a map on causal dual operads that reverses the direction of this. But all maps of causal binary operads are induced from quadratic data. That's exactly what I wanted to avoid to talk about. It's the one reason why we use the word binary here is to avoid this. Yes. So. Okay. So naturality means that, let me just make sure that I use the same thing as here. So since I have a morphism like this, so I have here the category of P algebras, of P Schrick algebras. And given this morphism, I can do a restriction of scalars and end up in Q Schrick algebras. And our theorem says that this is equivalent to FM formal moduli problems over the causal dual of P Schrick. This and yeah. So okay, our theorem also says that Q anti-Schrick algebras are equivalent to FMPs over Q. And exactly the thing that we did before with associative and commutative, what we can do is if we start with a P formal moduli problem, we can also evaluate it at Q algebras just by restriction. So in some sense, both these maps are restrictions. Yes? Well, in the sense that if you take the appropriate model structure on coalgebras, the the Valette argument tells you that these two, that they are equivalent. Yes, but I don't know if you gain something from. If you can get something just directly going to coalgebras without directly passing by algebras. Sorry again? Right. Yeah, I have to say I didn't really think about this. I can try to think about this after. Yeah, I for right now I don't know. Maybe. Yeah, maybe there's just no obstructions there. But I'm just saying that I don't want to commit to an answer to that particular question. Okay, so what? Right. So how does this equivalence actually work? So maybe I will not explain why that's an equivalence, but I can at least show what the functor looks like, at least how to compute the functor on some object. So the functor Mark-Cartan, say from pre-Schick algebras to formal moduli problems over P. What you do is let me keep the conventions from Lie algebras and commutative algebras in the usual story, where here this is the commutative operad and here this is the Lie operad. So I will call elements here G, and I will call the Artinian guys there A. So what do we want to do? We want to construct something that I will call Mark-Cartan of G, that will be something that will take small P algebras and will give you some space. And the way you do it is you can almost follow the following algorithm. So if so first you will require small algebras to be finite of finite dimension in every degree. But maybe homologically, but maybe A itself is not. So if A is not of finite dimension, replace it by an equivalent P infinity algebra that is of finite dimension. So in general, you will. I don't think there is any reason in general why you could find a strict P algebra that is of finite dimension, just because the homology is. But one thing that you can always do is to take homotopy transfer from the homology. So even in the commutative case, I don't think this is something that you can do in general. So then you use exactly sort of the fact that Bruno was mentioning, which is that G tensor A is a L infinity algebra. And it's not very complicated to see why this is the case. So this is naturally an algebra over. So this was a P-Schrick tensor P infinity. So this acts here, and there is a map from L infinity to this, which you can write the formulas, but the conceptual, I guess, a formal reason why this map exists is you look at the map of operads from L infinity into P Schrick tensor. So this is level-wise tensor product from P Schrick to tensor P infinity. Yeah, arity-wise. You're right. It's more correct. So this is just more cartons in some Lie algebra, which I'll lazily just write as a Hom sigma of the dual of com. Maybe there is some degree shift into this P infinity. And there is a Hom tensor junction, so you can actually just move this one here. So this is more carton elements on Hom sigma of the dual of this to P infinity, but then you use again just the bar-cobar to isomorphism story and conclude that this is just the same as Hom of operads from P infinity to P infinity. So you could take here the image of the identity via these identifications. The linear dual of the commutative algebra. So arity-wise linear dual. Yeah. So this is not actually the way that you define the functor, but I'm exhibiting its behavior, or how to compute the image of the functor MCG on a certain small P algebra. So yeah, we're almost defining the functor in some sense. And finally, so MCG of A, which is now a space, is equivalent to indeed some. So the reason why we call it Maurer-Cartan is because this is the Maurer-Cartan space of exactly this, that L infinity algebra over there. Yeah. So right. Okay, so in principle, I have 4 minutes, but I will go a bit over time. So what I wanted to get is that we've been talking about pre-Lie algebras all this time. So the pre-Lie algebra is Zool. So this is a result from Chapoton Livernet. Sorry? Yes. It's definitely not. Yeah, the pre-Lie operad is Kozel, and its Kozel dual is a very funny operad. It's the operad of permutative algebras. So this is binary quadratic. So its Kozel dual is also binary quadratic, and these are algebras that satisfy. So what is a perm algebra? So it's perm algebra. It's an associative algebra. I'm running out of letters. X such that x, y, z, so I don't need to put parentheses because it's associative, is the same as x, z, y. So it's not commutative, but as long as you fix the first element, everything else is commutative. And it's an operator in sets even. So what you actually can then you ask me what can we do with the permutative algebras? Well, you can do something very interesting. You can also, but no. So given a perm algebra X, define let's say there is an opera that we can define using the permutative algebra X. We can define an opera Pn that is in every arity equal to X. And this defines an opera with partial compositions equal, every partial composition equals the product in X. So this is actually something that you cannot do with an associative algebra. So if you think about this, a permutative algebra has two properties. So it's associative, and this kind of represents that if you define an opera using partial compositions, there's two axioms. There is the one that I will call the associative axiom, which is when you put three trees kind of one on top of the other, and it tells you that doesn't matter in which order you put them. But then there is the sequence, people call it, I think, parallel axiom, but here we can call it the permutative axiom, which is when you have one here and one here, it doesn't matter which one you plug first, but as long as the base one stays the same. So this is exactly the permutative relation. And it turns out that this is kind of it's a kind of causal dual to the existence of a Pauli algebra structure on the deformation complex. Now, I just need to make a quick decision on how exactly. Yeah. All right. Right. So in particular, this tells you that if I take an operand, I can take the tensor product of an operand with a permutative algebra everywhere, and I stay, and it remains an operand. So now, following what I was saying before, the formal moduli problem associated with the Lie algebra P infinity, say V, as before, but so always untwisted. So seeing this as a permutative formal moduli problem associated to the Pauli algebra here is given by the functor f that sends small permutative algebras to spaces that will take a permutative algebra A here, an Artinian small permutative algebra, and we'll map it precisely to the mapping space of operads from P infinity into endomorphisms of V tensor A. So maps in the So it's simplicity enriched. So it's actually home tensor this simplicial set. Yeah. So this tells you exactly that even in this permutative sense, this Lie algebra does really represents deformations along the zero map. And there's also something slightly funny that happens, which is the fact that whenever you twist here by a Mark-Cartan element, which is not the zero Mark-Cartan element, so somehow now you want to in the FMP side, it corresponds to trying to deform to do some deformation along this new morphism. And for this you kind of need a unit on your permutative algebra to kind of tensor to this unit. But one thing that I embarrassingly took way too long to realize is that actually unital permutative algebras are just commutative algebras, because you can put the first thing being equal to 1, and this is just commutative algebra. So that's why you don't actually get particularly new information if you do not deform along the zero map. Still, this does capture a lot of information, because in some sense, all algebraic structure is a deformation of the zero map. You can put a formal parameter and just send it to 0. And yes. So even though I'm over time, I really need to state one result, because I said literally nothing about characteristic P, and I should at least mention.
It was not mandatory.
I know, but now I feel the responsibility of. Right. But so there is this theorem that I definitely have to mention. It's from 1 or 2 years ago, from Lucas Brandner and Akil Matthew. And I will write it and just say by words what I mean by this. So in positive characteristic, actually in any characteristic, so if characteristic of K is equal to 0, you can still define formal moduli. So forget about operads now. It's just commutative formal moduli problems. You can still define formal moduli problems over the field K. The Schlesinger conditions and everything stays the same. The question is, what's the input? And in the input, you don't actually want to take differential graded algebras. Maybe you want to consider either simplicial commutative rings, Artinian simplicial commutative rings, or infinity rings if you're doing the spectral case. What they show is that here, this is equivalent to some notion of partition Lie algebras. And this notion of partition Lie algebras does coincide with ordinary Lie algebras in characteristic 0. But in positive characteristics, so this is actually a very hard category to define. So you don't even, so first of all, it's not, it gets a lot harder because these are not algebras over an operad. They can be defined as algebras over a monad, but even the monad itself is slightly tricky to define. So at the end, these remain kind of very elusive objects. So one thing that, yeah, this is a mini course, I should be talking about more classical stuff maybe, but one thing that we did with Brandner and Nathan was to try to find some operatic-like expression for this. So, and this will end up having to deal with constructing injective resolutions of the commutative operad. But okay, I will definitely stop here. Thank you very much. Yes, what did I say?
No, I thought that you meant that it's in progress or
No, oh yeah. I guess the understanding of partitionally algebras is in progress, but the description of seeing this category as kind of a category of algebras over an opera is already on the archive for since 3 or 4 months ago, I think.
is there any question?
Daniel put his hand first.
Right. So you were saying, okay, so you can actually compute this function or this marker, right? Because the marker is using twisted and infinity. You can compute the geometry groups of groups, right? So do you have an interpretation of hierarchy groups? Because from point of view infinity categories, like in the end you look at the zero edge, your format distributions up to equivalencies, but then hierarchy.
Yeah, it's
What classes of morphisms, A1 or something like that?
it is an infinity groupoid, and it has interesting higher homotopy groups.
Concrete,
I mean, I guess
in terms of the formation of
I guess I would not say anything additional to what has essentially been discussed in both Alexander's and my lecture. I mean, particular to this case. The one tiny remark is that there is no, so since things are nilpotent, there's just no worries about completions or anything. So in the commutative case, essentially your filtration is anyway by the powers of the maximal ideal. So, but Muriel? Definitely, there is a connection between this and restricted Lie algebra. So, no, yes. So actually, the way I said that this is a bit elusive, but you can actually describe the monad. So at least if on V, so let's maybe say it doesn't change much if it's the spectral or the case or the other one. But so imagine that you have V K module and it's maybe negative degrees, finite dimensional, to be sure, because then you extend it by filtered co-limits and so on. So there is a monad that they call Lie pi, which on V will end up doing something like tensoring up with maybe they actually need to take a simplicial version of V and then totalize it at the end, and here tensored up with N, and there are some homotopy, some strict fixed points in the normal case, and some homotopy fixed points in the spectral case, and here there is some partition complex. So a complex on the partition poset. Okay, then, so this is also simplicial, so then you need to totalize again. But so there is something like this here. So in some sense, restricted Lie algebras are very level 0, kind of pi 0 part of this. More concretely, every partition Lie algebra will give rise, in some sense, to an underlying restricted Lie algebra, but it contains a lot more structure. John?
First, what was the key case? They are linked with the function.
What's the link with PKs? What?
If you set overall, I think in characteristics you do, you take the partition P partition.
Right. No. So here it's really partition. So yeah, it's partitions of N. So think, yeah, yeah.
That might be
Ah, yes. So you're trying to push out the two things, right? Yes. Yes. There is a there is a kind of an obvious. So yeah. There is an obvious push out one can try to put. It's not completely clear that that everything works wonders. So there's just some like lots of homotopical issues that will not exist for that do not exist in characteristic 0 and exist in characteristic P. So for instance, if you have an opera P and you take something like restricted algebras over P, this will not this will not be quasi-isomorphism preserving. I don't know. This is of course something that is still very recent and has to be. Yes.
you have a formal module, but you know that this E algebra has more as it might be an associative algebra. What do you get as information to the formal? What can you hope? You can define this sort of bigger category, but what information do you get on the problem? The fact that there is no.
Yeah. I guess I cannot give you an answer of this in this way. Yeah, it depends a bit on the concrete case. If you're thinking about the complex varieties case, I don't know. I kind of took this as an example that I never studied that thoroughly, so I don't know what from there. I don't know. I don't know. I need to think a bit more how to answer that question.
Probably something very basic about so I guess that somehow the problem is meant to tell us the algebra is very formal or not.
If the algebra is formal,
Yeah,
you. Sorry, you mean seeing if this if an algebra that you take here on this side, if it,
so like for example for the Ocean complex the associative case, like this is meant to be called I can find instructions from algebra here, and it's associated to a formal modulation property, right?
right?
Okay, so I guess how might be written in the formal modulation.
Yeah, it's
In the end, the question is, say I want to know if the algebra is formal, can I use a version of the correct version of
yeah. So there's much to say about this. So first of all, in the infinity categorical sense per se, notion of well doesn't make much. Yeah, it's not so so relevant, say. But then direct relation to formality, I think, will anyway always pass by a sort of argument that I exhibited in the second lecture. I don't know exactly. I have no idea what's how to interpret this in characteristic in positive characteristic, because I've never thought about even about formality and positive characteristic besides. It's what Geoffroy was saying and things of the sort, or Paulo. Yeah, so
Is there any question online? No, not all. I propose that we thank